So far in the course, we started off with a discussion on dimensional analysis and then dimensionless groups and correlations between them. We had looked at different kinds of flows and the factors that affect the correlations for mass, momentum and energy transfer. The dependent dimensionless groups, the dimensionless fluxes and the independent dimensionless groups, ratios of convection and diffusion and different kinds of diffusion. And then we had taken a closer look at mass, momentum, energy diffusion and dispersion. Diffusion due to the molecular fluctuating velocities, dispersion due to the fluid fluctuating velocities. In this class, we will start looking at unidirectional transport. Unidirectional transport means that there is transport only along one coordinate direction. Okay. First, I will consider a Cartesian coordinate system, where that transport is along the z direction in this case. And so, the fields, the concentration, temperature and velocity fields, they are continuously varying functions of that particular coordinate. And I told you that this description is valid so long as the length scale of the flow, the length scale of the transport process is much larger than the molecular scale, which is the mean free path in gases or the molecular diameter in liquids. So, these vary along one spatial direction and they could vary in time as well. Okay. And there could also be forcing in the sense a reaction could result in the generation of mass of a particular species. Okay. So, that would act as a source of mass of a particular species if that is the product, and it could be a sink of that mass if it is a reactant. Similarly, locally you could have heating or cooling, for example, through exothermic or endothermic reactions. These would act as sources or sinks of energy. Source and sink of momentum are due to applied what are called body forces. Okay. In each of these cases, the source has dimensions of mass, momentum or energy per unit volume per unit time. So, these are basically intensive quantities. They are defined as the amount produced, mass produced, energy produced, the force, mass or energy produced per unit volume per unit time, or the force per unit volume per unit time. Okay. So, these are the ingredients. Okay. There are temperature fields or concentration fields or velocity fields. These there are two kinds of variations. One is due to the fluxes. Okay. As momentum and energy are transported, or mass, momentum and energy are transported across surfaces, there is a flux. That is a surface flux that is proportional to the surface area. And then there are body forces or sources which are proportional to the volume. Okay. So, these are the ingredients, and so what we do is we write a balance equation for a particular differential volume. Okay. Take the limit as the size of that volume goes to 0 in order to convert the balance equation to a differential equation. Okay. That differential equation contains derivatives with respect to both position and with respect to time. This differential equation can then be solved subject to boundary conditions to derive the solution over the entire domain. Okay. So, there are two steps there. One is the balance over a differential volume giving rise to a differential equation, and then the integration of that equation to find out the variation over the entire domain. Okay. So, we will go over those two steps one by one in the during this course. Okay. So, first we will just consider mass transport. Okay. Consider a domain. Okay. I will consider z as the direction across. Okay. Z is the direction in which there is variation. Okay. So, you could for example have the concentration field for example varying in some way between these two. Okay. Now, how do we derive an equation for the concentration? So, we will take a differential volume. Okay. Okay. Of area A perpendicular to the z direction and thickness delta z. Okay. Area A perpendicular to the z coordinate and thickness delta z, and we will write a balance condition for that. Okay. We will write a balance condition for that. Okay. So, this is so we will. So, this is the location z, this is the location z plus delta z, and the difference between these two is delta z. Okay. The total mass in the differential volume is the concentration times the volume itself. Okay. Mass is equal to C of z t times delta z times A. Okay, that is the total mass in the differential volume. Okay. What is the balance condition? Okay. The mass conservation condition is that change in mass in differential volume is equal to mass in minus mass out, okay, plus production. Of mass in the differential volume, the source of mass. Okay. So, that is the conservation condition. Okay. What is the change in mass in a time delta t for example? Okay. In time delta t in this differential volume. The change in mass in the time delta t within this differential volume is going to be equal to the concentration at z t plus delta t minus the concentration at z t, change in concentrations times the volume which is A delta z. That is the change in mass in a time delta t. Okay. What is the mass in? Okay. So, if I just expand out that differential volume over here, there is a mass coming in because of the flux at the surface at z. Okay. Recall that I had said the flux is positive if it is in the plus z direction. Okay. The flux is positive if it is in the plus z direction. Okay. Therefore, there is a change in mass, the mass in is because of the mass coming in at z. Okay. So, mass in is equal to the flux at the location z times the surface area, okay, times A times delta t. Note that the flux is mass transported per unit area per unit time. So, I have to multiply the mass, the flux by the area and by time in order to get the mass coming in. Okay. Similarly, mass out, mass decreases in the volume because of the flux that is leaving at the location z plus delta z. Okay. Therefore, this is equal to J z at z plus delta z A delta t. Okay. So, those are the components of the mass in and mass out at the surface. I should note here that because there is a variation in the concentration in only the z direction, this is unidirectional transport. So, there is a variation in the concentration only in the z direction. That means that the flux is also only in the z direction, in this case of unidirectional transport. Okay. So, that is the mass in and mass out, and finally, we have the production. Okay. Recall that I told you that the production is defined per unit volume per unit time. Okay. So, this is going to be equal to the rate of production of mass at the location per unit volume per unit time multiplied by the volume multiplied by delta t. Okay. So, that is the rate of production within this differential volume, because I have defined S as the production per unit volume per unit time. So, these are the different terms in the equation. Okay. These are the different terms in the equation. I put it all together. Okay. C at z t plus delta t minus C at z t into A delta z, that is the change in mass in the differential volume, is equal to the mass in, which is J z at z A delta t, okay, minus the mass out, which is J z at z plus delta z A delta t plus S of z t A delta z delta t. Okay. So, this is the balance equation for the differential volume, volume A delta z over a time delta t. We divide throughout by volume and by time, okay, to get a difference equation. Okay. Divide by volume and divide by time to get a difference equation. If I divide by A delta z delta t, I will get C at z t plus delta t by delta t. This is equal to J z at z minus J z at z plus delta z divided by delta z. Okay. A and delta t will cancel out, and then I will get a final plus S of z t. Okay. So, this is the mass balance condition. I have done a balance for the mass in a differential volume over a time delta t, the change in mass in the differential volume A delta z over the time delta t divided by A delta z and divided by delta t. Now, I take the limit delta z goes to 0 and delta t goes to 0. Delta z goes to 0, I get partial C by partial t. Delta z goes to 0, j at z minus j at z plus delta z. Okay. Note that j at z plus delta z minus j at z is the partial derivative. So, this is equal to minus partial j z by partial z plus S of z t. Okay. So, that is the mass conservation equation in differential form. Okay. This is the mass conservation equation in differential form. Note that it contains what are called partial derivatives. Okay. Partial derivative with respect to t means, for example, that I keep z a constant and vary t. Okay. So, in this particular case I kept z a constant and taken the difference between two successive times. Similarly, the partial derivative with respect to z is taken by keeping t a constant. Okay. So, this is when you have a partial differential equation where you have multiple coordinates. In this case, position z is one and time t is the other. Okay. So, this is an equation that contains both z and t. Okay. Okay. Now, we have to substitute for the flux. Okay. We have to substitute for the flux. Fixed law of diffusion, J z is equal to minus d partial c by partial z. Okay. J z is equal to minus minus d partial c by partial z, where d is the mass diffusion coefficient. Okay. So, if I substitute that in here, I will get partial c by partial t is equal to plus. Okay. You have a minus sign here and you have a minus sign here, and therefore, the final equation will be plus partial by partial z of d partial c by partial z plus s of z t. If the diffusion coefficient is a constant, if the diffusion coefficient is independent of position, then this equation I can take the diffusion coefficient outside and I will get, okay, if okay, I will get partial c by partial t is equal to d times partial square c by partial z square plus s of z t. Okay, so, this is the mass conservation equation for unsteady unidirectional transport, where there is a variation in concentration in one direction and in time. Okay, there is a variation in concentration in only one direction and in time. Okay. Okay. So, this is for mass transport. Energy transport, okay, similar configuration. Okay. Let us say z is equal to 0 and z is equal to h. Okay. There is some variation in the temperature between these two. Let us say I have T naught and T h here, some variation in temperature, and there could be a variation of temperature with time as well. Okay. The temperature could vary with time as well. Okay. Once again, I take a small differential volume, okay, of height delta z and cross sectional area A. Area perpendicular to the z coordinate is A and this is z. Okay, so, let me expand out that volume here for easier visibility. Okay. This is at z, this is at z plus delta z. Okay. And the cross sectional area of this volume is A. Okay. The energy balance condition, change in energy in time delta t is equal to energy in plus production of energy. So, that is the balance condition. Okay. What is the change in energy in a time delta t? Okay. Change in energy this will be rho Cp t at z t plus delta t minus this is the change in the energy density. Rho Cp T is the enthalpy density. I have to multiply this by the volume, okay, A delta Z, okay, to get the change in the energy. Okay. So, that is the change in energy in the differential volume. Okay. What are energy in and energy out? Energy in is due to the heat flux coming in at the surface at Z, Qz at the surface at Z. Okay. This is equal to Qz at the surface at Z. Flux is per unit area per unit time. Therefore, I have to multiply it by the cross sectional area A and the time delta t. Okay. That is the energy in, okay, at the surface at Z, because Qz is defined to be positive if it is upward. Okay. Similarly, energy out is equal to Qz at Z plus delta Z. A delta t. Okay, so, that is the energy coming in and the energy going out. Okay. And finally, the production of energy. Okay. Okay. Production of energy is equal to an energy volumetric energy source, energy produced per unit volume per unit time, times A delta Z delta t, where SE is an energy produced per unit volume per unit time. For example, by a reaction process, if it is exothermic, then SE will be positive, if it is endothermic, it will be negative, or you could have phase change processes as well, okay, which are producing or consuming energy. So, the general form of the production term will be a source times the volume A delta Z times the time interval delta t. Okay. So, that is going to be the form of the energy production or consumption. Okay. So, putting all of these together, okay, the left side is rho Cp t. Okay. Note that in general rho and Cp could be functions of position and time. Okay. So, all of these three will in general be functions of position and time. So, I will just use the enthalpy density for that. Okay. Enthalpy density H is equal to rho Cp t. Okay. Therefore, the equation will be of the form H at Z t plus delta t minus H at Z t into A delta Z. That is the change in enthalpy in a time delta t. Okay, the change in enthalpy in a time interval delta t is the final at time t plus delta t minus the initial at time t times the volume, okay, because H is an enthalpy density. Energy in, which is Qz A at Z A delta t minus the energy out, which is Qz at Z plus delta Z A delta t, okay, plus the source, which is SE A delta Z delta T. Okay. Source per unit volume per unit time multiplied by volume multiplied by time. Divide throughout by volume, divide throughout by time. Okay. And I will get H at Z T plus delta T minus H at Z T by delta T is equal to Q Z at Z minus Q Z at Z plus delta Z by delta Z plus AC. Divide by volume, divide by time, A delta Z delta T. Take the limit as delta T and delta Z go to 0, partial H by partial T is equal to minus partial Q Z by partial Z, because Q Z partial Q Z by partial Z will be Q Z at Z plus delta Z minus Q Z at Z, okay, divided by delta Z. This is the negative of that, okay, plus AC, okay, or partial of rho Cp T by partial T is equal to minus partial Q Z for Q Z. You have to substitute Fourier's law. It's equal to minus K by partial Z, okay, and you will get partial of rho Cp T. Okay. You have two minus signs here, so if you multiply those two you will get a plus sign. You have two minus signs here, so if you multiply those two you will get a plus sign. So, I will get partial by partial Z of K partial T by partial Z plus SE. Okay, so that is the energy conservation equation for the general case. Okay. That is the energy conservation equation for the general case. Now, this energy conservation equation can be simplified if rho Cp is equal to a constant. Okay. Rho is a constant for an incompressible fluid. Okay. Typically, for most applications, rho will be a constant unless the velocity is comparable to the speed of sound. Okay. Unless the velocity is comparable to the speed of sound, you can consider the density to be a constant. Okay. The specific heat is also a constant in many situations of practical interest. Okay. So, for example, the specific heat of air will vary by about a percent when the temperature goes from 0 degrees to 100 degrees centigrade. Okay. It is only about 1% variation when the temperature goes from 0 degrees to about 100 degrees centigrade. In liquids, it varies even less. Liquid water, for example, specific heat varies by 0.1%, 0.1% when it goes from 0 degrees to 100 degrees. Therefore, in many cases, this can be assumed to be a constant, in which case you can take it out of the derivative sign and write partial T by partial T is equal to 1 by rho Cp partial by partial Z of K partial T by partial Z plus Se by rho Cp. And since this is a constant, okay, you can further simplify this as partial T by partial T is equal to partial by partial Z of K by rho Cp and this is equal to the thermal diffusivity. Okay, this is equal to the thermal diffusivity. So, the equation becomes partial T by partial T Further, if the thermal diffusivity is also a constant, okay, then I can take it out of the derivative, okay, and I will get partial t by partial t is equal to alpha partial square t by partial z square plus S e by rho C p. Okay. Note that this has the exact same form as the equation for the concentration, which was partial C by partial Z is equal to d plus S, okay, for constant diffusivity, and in this case it had the form partial C by partial T okay. So, when expressed in terms of the diffusivities and the sources and sinks, the equations for the concentration and the temperature have the exact same forms. So, we will continue this in the next lecture. I will derive the momentum conservation equation, which will also turn out to have the same form, and then we will discuss the general form of these conservation equations. We will continue this in the next lecture. We will see you then.